We're going to learn a new kind of proof now and start the formal proof section after all the stuff that we've done with sets. And this is called mathematical induction, and essentially it is a way of proving math statements true for all integers. A way of proving true for all integers. And that's kind of a key thing here. If you're looking for styles to prove and you have increments by integers, this can be very, very useful. But it all depends on integers. So an example of this would be this thing. 1 plus 2, or 3 plus 5 plus all the 2n minus 1s is just equal to n squared. This is an obvious result if you just kind of look at the patterns here. You might not have known this one or even remembered this one, but the p of 1, meaning the first one, is just 1, and that's equal to 2 times 1 minus 1, which is also equal to 1 squared. And as we look at the ordinality of what we're substituting, this 1 is the same as this 1 and this 1. Now if I kind of keep going with this, I would get p of 2 is the same as 1 plus 3, that's the first two terms, and that's the same as 2, or sorry, that's the same as, my bad, 1 plus 2 times 2 minus 1, because that's the second term, and that's the same as 2 squared. What it's important to note here is that this 2 is essentially the same as this 2 and this 2. This is kind of the integer part of this. It's increasing in a very predictably ordinal way. P of 3 is the same as 1 plus 3 plus 5, which is 1 plus 3 plus 2 times 3 minus 1, which is equal to 3 squared. Once again, I see those 3's there. This 3, this 3, and this 3. And you're building, like, this right here, this part where you're kind of building it based on the previous one, this is called recursive. Whereas this one right here is called inductive. This is sort of a bold statement made where you don't need to know the previous element. Now, if we want to prove that this is true using induction, there's a very systematic way to do this. Okay, for the first step, you're going to prove that p of 1 is true. Well, that's trivial. That's trivial because you just can show that right up above. We actually showed that p of 1, which is the first term, is equal to 1 squared. So that part's done. Now, the next one you prove is assuming p of k is true. Show that p of k plus 1 is also true. Now, Mr. Keelan has a problem with this one, and I can understand where the problem is. So rather than this, let's think about this as an if-then. If p of k, then p of k plus 1, which is really what this is saying. It's not saying p of k is true. It's saying if it were true, then we could definitely show that p of k plus 1 is true. So this is kind of a two-step process. It's really one step, but assuming p of k is true means that we have to know what that means. That means that 1 plus 3 plus 5 plus all the way up to 2 times k minus 1 equals k squared. Assuming that that is true, we now need to show that p of k plus 1 is true. Well, that means they need to show that 1 plus 3 plus 5 plus 2 times k minus 1 plus 2 times k plus 1 minus 1. I'm going to show that that's equal to k plus 1 quantity squared. Well, I can take this left side and substitute this with k squared because I know that from the previous step. So I have k squared plus, and if I distribute this, I get 2k plus 2 minus 1, or plus 1. And then I get k plus 1 quantity squared. So in showing that that's equal to k plus 1 squared, I just need to take this left side, substitute it, and show that I get this.
but it's...
I'd say we're done, but now Clay wants some physics help, so I guess we'll pause. Now essentially what I want you to see with this is that it collapses an infinite number of steps to a finite number. Oops, that's not infinity, that's percent. Infinite steps become a finite number of steps. Actually become just a few steps. And so any process that can kind of extends out to infinity, you prove P of 1, and that then shows that P of 2 is true, which then shows that P of 3 is true. And that's the essence behind this. By proving the case for P of k, showing P of k plus 1 is true, you've shown it for all of them throughout infinity. So number 2, here's another example. 4, I guess I should put a number 1 on the previous one. For n contained in the natural numbers, I can show that 1 plus 2 plus n is equal to n times n plus 1 over 2. This is an old one. This is actually the summation formula, or a result of the summation formula. So anyway, if I show P of 1, and I just kind of start this process, I can say 1 equals 1 times 1 plus 1 over 2. And that's check. Okay, got that. And then I say if P of k, and P of k means this, it means 1 plus 2 plus k is equal to k times k plus 1 over 2. Then let's show P of k plus 1. Well, P of k plus 1, I'm just going to take the left side of what that means, 1 plus 2 plus k, and then plus another k plus 1. And let's substitute that, and we want to try to make that equal to what would happen if I substitute k plus 1 in the left side, or in the right side here. So I'm trying to show that that would be equal to k plus 1 times k plus 2 over 2. And if I can show that, then I've got it. So essentially I'm going to take this piece here, all this stuff here, and let's substitute k times k plus 1 over 2, and then we're going to add the other k plus 1. So let's add these up within the least common denominator 2. I've got k times k plus 1 plus 2 times k plus 1 over 2. Factor out a k plus 1 in the numerator, and I get k plus 1 times k plus 2 over 2. And that is done, because that matches what we wanted. Seem easy? Should. Let's make it a little bit more difficult. So I felt like I gave you 2 easy ones. I'm going to give you a hard one here. Because some of these can get pretty difficult, and you just kind of have to play with them, like many of the ones we've done. We're going to prove that for every positive integer, and the way I can say this mathematically, I'm kind of using a lot of symbols here, but I can even do this for every k, such that k is, sorry, let me say this, for every k in z, such that k is greater than 0. That's a way of saying positive integers. But I'll just keep that up top because I'm not going to use the k. Actually, it should be n for every positive integer n. I just use that in the rest of the proof. There exists an n-digit number divisible by 5 to the n, all whose digits are odd. So when you're trying to figure out what this is saying, it's helpful to start with a base case. If n equals 3, for instance, and then my 5 to the n is equal to 5 to the third, or 123, and there should be a 3-digit number divisible by 5 to the third. That's all whose digits are odd. Well, 125 is not odd, and if I take it and I multiply it by 2, I get 250. That doesn't work. But if I multiply it by 3, 125 times 3 is 375, and that works. We can try this with n equals 4. 5 to the 4th power is 625. 625 doesn't work. And I'm looking for a full 4-digit number anyway. So if I try by 2, if I try by 3, I could keep going all the way up until you get to 625 times 15. And you're going to get 9375, and that's one whose digits are all odd. n equals 2 should be relatively easy. I got 5 squared is 25. 25 times 1, nope. Times 2, nope. But times 3, I get 75. 25 times 3 is 75. So I've got these digits that match the number of digits for the n. And I can prove this with induction. This is a relatively difficult one, but I want to show you kind of how this works. So p of 1, n equals 1, and a one-digit number divisible by 5 to the n, by 5 to the 1, and that is 5 itself. So that one's done. Okay, then I say if p of k. So when I say if p of k, I will assume that I have a number that's equal to some digits a1, a2, a3, all the way up to ak, and these are all odd digits. So that's actually the composition of the number itself. Those aren't being multiplied. But that's equal to some 5 to the k times m, where m is not divisible by 5 to the k. So if I look back up here, these were my capital M's, my 3, my 15, my 3. Basically, how many times are we multiplying 5 to the k to get that number that's all odd digits? So I would sit on this for just a minute and kind of look and see what this is saying before we move on. It's very important just to kind of pause the video, check that you see that this capital N represents your number that makes this true, your number in n digits that's all odd. And your 5 to the k times m, this is similar to your 125 times 3. And clearly that 3 is not divisible by 125. So we're going for small numbers here. Okay, moving on. P to the k plus 1 is, well, p to the k plus 1 includes one more digit. So it is either 1 and then a1, a2, all the way to ak. And we could say that that's equal to 1 times 10 to the k plus the 5 to the k times m. Now, I want you to hold on that for a minute and realize what I'm doing is I'm essentially building my next number using the previous one. I'm saying that I'm going to have to add 10,000, or not 10,000, but 1 followed by k zeros to that. That's kind of setting it up. Basically, I'm saying 1, 0, 0, 0, 0, 0 plus a1, a2, a3, a4 to get that next one. Now, you may say, okay, I can buy that, but first, why does it have to be a 1 before it? Well, it doesn't. I'm actually going to have to show that it could be 3 in front of it. It could be a 5 in front of it. It could be a 7 in front of it. Pick another color. I'm going to go orange. And it could be a 9 in front of it. Those are the only odd digits. So if I go back to the 3 case, that's going to be 3 times 10 to the k plus 5 to the k times m. Well, if I factor a 5 to the k out of this numerator part, or out of this thing, I get a 5 to the k times 1 times 2 to the k plus m. Let's see what happens when we keep doing this. I'm going to take a 5 to the k out of here, and I get 3 times 2 to the k plus m. And then for this one, 5 times 10 to the k plus 5 to the k times m is equal to 5 to the k times 5 times 2 to the k plus m. This is 7 times 10 to the k plus 5 to the k times m, coming out as 5 to the k times 7 times 2 to the k plus m. And then lastly, 9 times 10 to the k plus 5 to the k times m, equaling 5 to the k times 9 times 2 to the k plus m. Okay, that's a lot of weird stuff here. But essentially what I have is, I know that all five of these have to have different remainders when divided by 5. All have different remainders when divided by 5. Because I've factored the 5 to the k out, and what I have is that they're all being added to some number, but one is 1 times a number, one is 3 times a number, one is 5 times a number, one is 7 times a number, and one is 9 times a number. So let's say that m, and this is a good time to kind of take a sidebar, just talk about modular arithmetic for a minute. Let's say that m could be, let's say m was 0, let's say m was 5, let's say m was 10. If m was 0, 5, or 10, or any of those, then this would be the one that would be divisible by 5. Now, if m was 1, 6, 11, those are all one more than a multiple of 5. So it would not be this one, it would have to be one of the other ones. But because of the nature of multiplying by 1, 3, 7, or 9, it could only be one of those. So I have 5 possibilities that are all different in what we call mod 5. One of them is 1 more, one of them is 2 more, one of them is 3 more, one of them is 4 more, and one of them is exactly 0 mod 5. They're all cycled through, kind of like the powers of I, but instead of 4, you have 5 here. So since one of them is divisible by 5, we know that one of them could factor a 5 out and become 5 to the k plus 1 times some number. And that's the pattern of 5 to the k plus 1 times some m. And that shows it. Your homework is a worksheet, which I'm going to have available here for you, and I'll have a copy on the web.